Swayam Prabha. Digital India. Educated India.
Hello, good morning. Today we will be discussing the fluid flow and conductance calculations in viscous flow region. If you remember, in the last class we were talking mostly on fluid flow concepts in vacuum system. While the level of vacuum is changing, the fluid flow also changes. So, I request all the participants to have a look of lecture number 31 before you read this, because you get a concept of conductance. These are only calculations based on some mathematics and physics, but the concepts of conductance and effective pumping speeds have already been discussed in the lecture 31. So, for this a prelude is very important. So, prerequisite. So, please again go through that lecture and come back to this. So, again I remind you, while vacuum level is changing, several things happen in the flow of molecules in the high vacuum range, flow of gases in the poor vacuum range, based on the conductance of the interconnecting pipe between the chamber and the pump. And I also told you in the last class, even if you have very good vacuum pump, very good chamber, you may still get very long pump down, just because you have not optimized the dimensions of the interconnecting pipe. So, you are paying for it. It is somewhat like you have very good cool drink, you have very good lungs power, but somebody has given a capillary pipe to drink. So, you cannot drink. So, it is the connecting pipe that plays a very important role. Now, in vacuum technology, it is customary to separate these regions flow point of view. Just like we have got separation classification on poor vacuum, medium vacuum, high vacuum, ultra high vacuum, extremely high vacuum, like that. Flow also initially little bit turbulent flow, then laminar flow, then molecular flow. These concepts have been discussed in the class 31. Most of the time turbulent flow we need not worry, because it happens in first few seconds. Though it is very important under choked flow conditions, when you are suddenly venting a chamber etc., which is a special case which we will cover after some time. First, let us understand typical design calculations and mathematical expressions required in designing the vacuum system network given certain pumps and given certain chambers. That is more important. Special situations like gas flows in inlets, choked flows, ventings etc., we will discuss after working out some examples of designs. Okay, that is only a transient phenomena. So, we need not worry about Navier-Stokes equations much here, because they are mostly used in turbulent region in high pressure systems. In fact, I told you, if you remember in the last class, as you come towards molecular flow from the viscous flow, we are entering into a new domain of flow. It is no more gas flow, it is called molecular flow. Molecules are flowing. There can be molecular flow in the reverse direction, even though pressure gradient is in the forward direction. So, very peculiar things are happening. So, flow is molecular flow below 10 power minus 3 torr, defined purely by the geometry of the conducting pipe. Whereas, little laminar flow which happens in the beginning, say maybe from 100 torr to or even for 300 torr, depending on the dimensions, up to maybe 10 power minus 1 torr. This is a laminar flow region. In fact, it may be 1 torr also, but sometimes if it is a very restricted thing and all, even 0.1 torr we will have some viscous flows. It all depends on the relative ratio of the dimension of the interconnecting pipe, which in fluid mechanics we call it as hydraulic diameter, with respect to the mean free path of the molecules, based on which we classified vacuum in the beginning. Now, we need to classify the flows also in that. So, it is the Knudsen number that plays very important role as you are proceeding in vacuum technology. It is not the Reynolds number alone. Initially Reynolds number is there, but afterwards we do not care about it. We do not care about viscosity, we do not care about gas dynamics, we do not care about fluid mechanics, that is normally being taught in the engineering. We talk about molecular engineering, though it is a flow of gas molecules, we do not say flow of gas, that we will see in the next class. But here we are in between turbulent flow and the molecular flow. Turbulent flow I am not covering because it requires a lot of mathematical things like fluid and Navier-Stokes equations, etc., programming, and simultaneously you have to solve momentum equations and continuity of equations, etc. But luckily we have a very great scientist Poiseuille for laminar flow. He has made a sort of analytical expressions for this region. So, that way he has given a very good tool with which we can calculate the flow parameters. In vacuum technology, what is the flow parameter? In the last class we have seen conductance, because flow of gases are taking place. In vacuum technology we call it as throughput, and there is a pressure drop which is the driving force, and the ratio is conductance. And this we have to get into vacuum technology, because we wanted to study the effect of connecting pipe on the effective pumping speed available for the real application with a given pumping speed having manufacturer's maximum pumping speed. So, you cannot phone to a manufacturer and say I am not getting vacuum. He might have given very good pump, you might have given a long pipe with a short diameter, you may be having a leaky system. So, your throughput is not the PV gas that is being pumped, and in a transient way, time as a function of time, pressure is falling. That is one application, but under constant load, constant pumping, the equilibrium pressure will be there. That is the process applications in vacuum distillations, vacuum drying. Continuously pressure is maintained at 10 torr, but pump is on, pressure should go down, pump can go up to 0.1 torr. Why it is not going? Continuous loading will be there. That loading can be from various sources, from the leak from the outside, from the degassing from the inner walls, from the evaporation of some unnecessary liquids, or from the evaporation of the known liquid which you are processing in pharmaceutical applications or intermediates, or it may be some other load which is coming from desorption, varieties of diffusion, all sorts of small loads will come into prominence as we go to high and ultra high vacuum. If you go to very ultra high vacuum, the entire throughput is not the PV gas or surface gas or leak gas or anything, it is the permeability gas. So, all this has to be thought over. Why I am telling in the beginning itself is, today I am not going to cover all that. We have already seen the concepts of fluid flow and conductance. Today we will go to the laminar flow region, which happens in the initial evacuation from atmospheric pressure up to a reasonable vacuum level. By that time 99.99% of the gas is removed from mass point of view, but no application has started. Volumetric flow rates are different, mass flow rates are different. Okay. Mass flow rates are related to the power of the motors. Volumetric flow rates are the displacement volumes of a known vacuum pump depending on its principle of operation. All that you have to keep in mind. We have already covered those things in 20 classes. So, after covering the conductance concepts, this is the ideal time to calculate using the standard Ohm's law, that is pressure drop is the potential drop, mass flow rate is the throughput, the ratio is the conductance. Just like V by I is the resistance, I by V is the conductance in electrical networks. Here I is equivalent to Q, that V means delta V, potential drop is equivalent to delta P. So, we have simplified it. But high pressures we cannot do this type of things, we have to use Navier-Stokes equations, because there is a turbulence, there is a sort of motion of the molecules in the perpendicular direction compared to the prior drop directions. All that will go into various types of energy consumption. So, energy equations have to be solved. So, all these things have to be like here only viscosity, various layers are flowing, whatever is very close to the pipe it will be stuck to the pipe, whatever is the central it will go freely, in between you will have a parabolic shape. This is a standard fluid mechanics, mechanical engineers know better, but otherwise with this lecture electrical and electronics engineers, if you want you go through the basic things of fluid mechanics, first chapter or laminar flow, that is enough. You do not go into the depth of various streamlines and turbulences and turbulent parameters, Reynolds not required. You need to read that much fluid mechanics of laminar flow before we get into this, and if you do not understand these things, you are free to contact me, I will be able to clarify your doubts. Okay. With this, today's lecture we will be conducting conductance calculations in viscous flow region, which is the starting point in the pump down characteristics of a chamber with a standard pumps in the medium vacuum range. The concepts that are going to be covered here are conductance calculation in the continuum flow. Continuum means the molecules will not be behaving individual identity, it will behave like a continuum, a gas. We will not have molecules, it is a gas. For example, flowing with the water I am drinking, actually molecules if I am drinking, but I am not saying I am drinking water, this is a liquid state, solid state I cannot drink of course, this is still dense, gaseous state, continuity is still there, actually there is no continuity between molecules, micron gap is there even here, but it is so small compared to the dimensions that we normally encounter, like a diameter of a pipe 1 inch dia 0.1 centimeter, whereas submicron micron level is the gap between two molecules. We do not consider that gap as the gap, we think as a whole it is a gas, that is called continuum flow. Under that continuum concepts, if it is a static gas, it is a fluid statics, if it is a dynamic, then it is called fluid dynamics, and if you calculate, it is called computational fluid dynamics, which is very popular. It is mostly used, laminar flow also you can use, but you have to use mostly, even liquids they use, or turbulent region only they use. We do not bother about that here, but in special situations, yes, space simulation chambers initially, silencers design of a huge chambers, you will have to do all that. Okay. So, that is one, today's class we are only bothered about continuum flow, and in that continuum flow how do you calculate the conductances, we will give the expressions. For brevity of time I will not be able to derive the Poiseuille's law, this is a standard thing, net may you put Poiseuille's law, you will get entire calculations, very simple, and if you do not follow you are free to call me anytime. And based on that effective pumping speeds you have to calculate, and we will give you some examples with which we will finally understand the effect of various dimensions of the interconnecting pipe based on conductance and pump down calculations, and we will be concluding with importance given to the interconnecting pipe, which is finally controlling the fluid flow, neither the pump nor the chamber. Okay. Later even leak we will consider it as a fluid flow, degassing we will consider the fluid flow as time passes in the system designs, but this particular block fluid flow we will only discuss about conductances, pipe dimensions, and this will help you. I told you in the lecture number 20, you will have to decide the purchase of the pump based on the interconnecting pipe. If a long pipe is inevitable, you will have to purchase the pump with a higher pumping speed, because it is more convenient to keep the pump on the ground floor and connect a load on the first floor for some reason, silence or something, you have to do that. So, you have to calculate all conductances in viscous flow is very important, and this is also important in high vacuum applications, because initial vacuum is only medium vacuum, 10 to 10 power minus 3 torr is the first phase, even though no application is there, but 99.999% of the gas is already removed, but no application started. It is like 99 runs, if you hit, he will not get century recognition. It is the last run that is very important. It is only not 1% of molecules which are still there, which is called residual gas, that if you do not pump, today we will not have TV tubes, we will not have computers, we will not have cell phones, we will not have particle accelerators, we will not have space technology. Okay. So, why I am covering this here continuum flow is this will be is very important for design engineers to predict the pump down timings in the initial hogging time. Hogging is nothing but initial evacuation, and semiconductor industry you have to be very careful to bring the -3 torr very fast in certain sections of the growth chambers or initial cleaning chambers of the silicon wafers. Similarly, process applications. Okay. Let us see. So, having explained the importance of it, I want you to understand little bit of fluid mechanics, very simple fluid mechanics, that is laminar flow. Because of lack of time, I am not going to details aspect. The same subject we are teaching 60 hours almost in one semester, 40-50 hours. So, I am not going into that. In a laminar flow, what happens? Mechanical engineers know these things very well. It is Reynolds number rho v d by mu, sometimes rho u d by mu. That d is nothing but diameter of a circular pipe. If it is a square pipe, it is the hydraulic diameter, which is given by 4 times the area, cross sectional area divided by the wetted perimeter. These things are known, in internet you can get these things. If this Reynolds number is less than 2000, which is normally true in vacuum technology in the initial evacuation story of a typical circular pipe, we do not use square pipes or anything, but in certain specific situations the geometry itself may be a wall or something, the itself may be a rectangular geometry, you will have to calculate. It may be giving lot of problems. At baffle, for example, you have to use the necessary hydraulic diameter there. Otherwise, it is only a diameter d if it is a circular pipe. With these things, this central figure shows the velocity profile, which is a parabolic in nature in a fully developed region in a pipe. For a layman's language, for non-mechanical students, the fluid that is flowing through in a laminar flow near the wall, it is dragged by the pipe, it is braked by the pipe. Drag is here, everywhere drag is there, layers are dragging each other, but here it is made to stop, because there is a lot of roughness of micron level. These molecules are at angstrom level, they will be circulating there itself near this zone. So, there fluid is virtually stopped. So, velocity is 0. In the central region of the pipe, it is going with a full speed, that is the maximum velocity. So, if you go through carefully, you will get this parabolic equation draw. Beautiful parabolic fluid velocity. This is a fully developed range. This is a well known concepts in mechanical engineering. So, these equations, based on that, Poiseuille, very famous engineer and scientist, he has defined from fundamentals point of view, which has been experimentally tested later for various fluids, for various viscosities, various diameters, various pipes, and it was confirmed that this analytical expression relates the volumetric flow rates with the pressure drop and the average pressure of a pipe. Pressure drop means across a pipe, the P1 minus P2, and the average pressure is in the center of the pipe, P1 plus P2 by 2. So, this is the standard equation we have been using in fluid mechanics, maybe little higher pressures, but velocities are small. So, that rho v d by mu is such a way that eta sometimes people call mu, it is a viscosity parameter. I am not going into the details of it. You can go through it very easily and use the necessary units carefully. Okay. Kinematic viscosity, dynamic viscosity, all these concepts you have to understand. But coming back to these equations, this is the thing, but we already defined conductance is q by delta p. So, conductance is nothing but pi d to the power of 4 by 128 into viscosity eta into L, length of the pipe, into average pressure. Okay. So, this is my pump, this is my chamber having at various pressures, there will be pressure drop, P 2 is always more than P 1, that is why flow is from this side to that side, conductance is given by this is the Ohm's law of vacuum technology. So, using this simple expression you can calculate, if you know the diameter of the pipe and length, you can easily calculate the conductance calculations of various pipes. Of course, you need to give little bit of additional precautions when it is bent. All these things have been worked out. There are still some situations where it is not worked out, that is still under research. In IIT Kharagpur, lots of students do this using various softwares developed, etc. Everywhere the CFD has become very popular, but I told you in the last class itself, in class 31, at high vacuum range it is not CFD, it is MFD, molecular flow dynamics. So, all these Navier-Stokes equations, Reynolds numbers, all these CFD is out, but in laminar flow if you want you can use, but you can use these simple equations. Why analytical equations are allowed? Just like V is equal to I R, if it is so simple, you do not take charge that is flowing, Coulomb's law, all that, you do not need to go to that much fundamental. Okay? So, this is how it is going on. These calculations are very useful in pump down calculations from 1000 millibar to 1 millibar, which is the viscous flow region. So, getting into little depth, you look at this figure, a typical vacuum chamber. Lots of things are happening here. There may be leak from the outside. It will leak because when you are evacuating, pressure drop is there. There may be degassing from the chamber wall. There can be some vapors coming out either from the known liquids which are there in the process, or a typical moisture that is somehow trapped when it is exposed to atmosphere, or one sweat of that fellow fell down when he was cleaning initially the chamber. One drop of sweat will be 1,000,000 drops equivalent volume, equivalent vapor load for high vacuum pumps. That is why you should be very careful in cleaning with water or anything. If you are forced to do that, you should again clean it with some ethyl alcohol or some other liquids, carbon tetra CF4, etc., carbon tetrachloride or something like that, which can evaporate fast. At the end you need to purge the things so that it is pure. Otherwise, you will never get vacuum below 10 torr. Pump is running, but as I told you in the rotary pump, water vapor can never be pumped easily unless you go to the gas ballast. So, all that problems will be there. So, better you understand these loads which are called throughputs. With all these loads, a total load is there. The pump has to overcome all these things, then only in spite of heavy loading a constant pressure can be maintained. If all these loads are not there in the control volume VDP, in the control volume load is coming, but whatever is going out is, if it is more, then pressure will fall down VDP, which is called pump down time. A typical ideal chamber without any degassing, no vapors, no leaks, when you switch on the pump, pressure will fall down, and that fall down can be computed knowing the control volume approach, a typical equation. I will not go into detail, if you just carefully observe you can understand. So, VDP, that means pressure drop as a function of this one, as a function of time, T is the time, is Q total into dt minus pumping speed. This pumping speed is here S, which is effective pumping speed, into the pressure existing at that instant of time multiplied by the dt interval. So, this approach when you do, the equation that we are getting here is VDP, which is nothing but T of PV. Normally volume in a chamber is constant, so V comes out, that is why it becomes VDP. Otherwise, you have to use P1, PV you have to differentiate, but in vacuum technology V is not inside, V comes out because a constant volume. A pump down of a chamber of volume is always constant, unless you have a variable volume. Sometimes it happens, there you have to take into account variable volume, that time you cannot take out of this differential. So, V dot dP is given by this. Under ideal conditions, what will happen? It will be only SP, because this Q total coming out of other parasitic loads are not there. Under that condition, if you do the simple calculations, say class 10th calculations, you will get the solution for this differential equation like this as a function of time. This at that time, what is the pressure? Okay. This I leave it to the students, how do you do that. So, if you want to know to get a particular pressure how much time it takes, you can use this equation, T is equal to V by S, S means effective pumping speed. But I now want you to remind you, this S is the effective pumping speed. As a function of time it may be varying, but in certain pumps pumping speed, if it is constant here, even though effective pumping speed cannot be constant, because conductance of this pipe is a function of pressure. So, 1 by S effective is equal to 1 by S plus 1 by C. I have told you in the last class. In this case I am not using S effective, we are using S because we are interested in pumping speed calculations and pump down times. I am taking it as effective pumping speed itself as S, but S dash is the maximum pumping speed given by the manufacturers. Okay. Then you can use this equation to calculate the pump down time required for a particular vacuum reaching. Alternatively, you can calculate pressure in a vacuum chamber or vacuum in a vacuum chamber as a function of time. So, these are the equations applicable in viscous flow range, because the conductance is calculated using viscous flow conductance, where viscosity is here and also pressure P is there. So, next iteration another pressure, average pressure. Manufacturer will say, sir, from 1000 millibar to 1 millibar constant pumping speed, even then you cannot take it as constant. We will see later special issues in the last later, after you get used to your conductances and some examples. We will give you some special situations like choked flows, variable pumping speeds, etc. Okay. We will keep that a little bit complicated issues towards the end, by which time you will get expertise in conductances and fluid flow applicable in pump down characteristics or pump down predictions of a vacuum technology, whether it is a space technology or semiconductor industry or a particle accelerator or a typical pharmaceutical industry or chemical industry. Okay. This I leave it to you. Now, programs also you can develop, so that you can nowadays everything is programmable, no? Because when intelligence becomes artificial intelligence and all calculations are programmable. So, of course, it requires lot of brain. So, you can do that when variable pumping speeds are available. Okay. So, these equations can be nicely used to predict the pump down time. We have done some pump down calculations for you just for the sake of it. You can do it in your own way. Take an example. Because of lack of time, I will not go into intricate details. A 50 liter volume is pumped down with a rotary vacuum pump starting from 1000 millibar up to 10 millibar. Why I have taken this? Up to 1000 to 10 millibar, you see a constant pumping speed, lucky. At least S effective cannot be constant, S is constant more or less, but within this conductance, which is a function of pressure, relatively higher pressure, conductance is also high. So, 1 by S effective is almost 1 by S type thing. So, I can take at higher pressures S effective approaching S, because conductances are so high. How does it matter if you are having 100 rupees, if 10 paisa is lost, does not matter. But if you are having only 1 rupee, 10 paisa is a mix 10%. Okay, you have to be careful. When pumping speed itself is falling, then the effect of conductance is going to be very, very prominent. So, I have taken this example to avoid little bit confusion in you, but real research is here. Manufacturer gives this pumping speed only, but you will be doing at 1 tar or 10 tar distillations. You have to know this pumping speed. You have to ask the manufacturer to give me this pumping speed, and at this pressure you have to calculate the interconnecting pipe conductances. Then come to this effective pumping speed, then calculate using that effective pumping speed, put it into that S here and calculate the pressure versus time curve. In this case, I have taken constant pumping speed is taken as 2 liters per second. Typical rotary pump manufacturers 120 liters per minute. Rotary pump manufacturers always give per minute, because then only they will get a higher value, and diffusion pump manufacturers always give seconds, 1000 liters per second, otherwise it would look astronomical. Okay. It all is a technique coming over a period of time. There are other issues in vacuum technology, we will discuss towards the end of the course. Okay. Now, this is how the pressure versus time curve getting from this equation. You can do it exercise by yourself, change the volume, change the pumps, etc. I leave it to you. So, it takes 115 seconds. So, if it is acceptable to your boss, otherwise what will you do? Either increase the pumping speed or increase the conductance. Either S or C, if you increase, S effective can be increased. 1 by S effective is 1 by S plus 1 by C. That is why these calculations are very important in viscous flow region to predict the initial vacuum pump down curves for high vacuum systems. And if it is a poor vacuum or process applications like pharmaceutical, chemical, it is the only application. There is no need like pre-vacuum. That is all the calculation need to be done. You do not have to bother about molecular flow calculations. So, same thing I have applied it, same equations I am reproducing for your clarity, and effective pumping speeds also I am calculating. I am changing a 1 meter dia, of course, I have taken, I am changing the diameters of the pipe. Then effective conductances change. If there are two pipes, you have to use again electrical networks. 2 conductances parallel, C is equal to C 1 plus C 2. If it is series, 1 by C effective is 1 by C effective plus 1 by C 1 plus 1 by C 2. So, depending on number of pipes and series calculations, you have to know first electrical network effective conductance, and depending on the pressure which flow region, you have to use the different equations to predict the conductances. Using all this, you calculate the effective pumping speeds. Using that and volumes, you calculate the pump down curves. If it is not acceptable, reiterate it and again change the pumping or something. This is called design in the viscous flow region. So, for a constant length, various diameters, these are the pump down curves. For a constant pump dia, various lengths, these are the calculations. That means, you will be able to tell your higher ups who are going to take a decision to purchase a pump or to accept this pump down time. If somebody says, no, 1000 seconds, no, I want in 10 seconds, a typical semiconductor industry, very fast, silicon wafer is kept inside, there is one initial chamber. I will discuss these things when we discuss semiconductor manufacturing. That has to be pumped very fast and clean it and send it to the next compartment, get valve is opened, and before even contamination from this poor vacuum takes place, wafer is already transferred. So many things are there in semiconductor industry or even particle accelerators or cell phone manufacturing, where the contaminations have to be there also conductance play an important role. If there are one vacuum here, other vacuum, what is the thing? If there are differential pumpings, what is the way? These conductances play an important role. Okay. So, with these ideas, I want to conclude in a process industry involving vacuum in viscous region. It also involves high vacuum region. In this particular class, I am talking viscous region, that is between 1 millibar to 1000 millibar. If you are using micron type of connecting pipes, it will extend up to 0.01, because it all depends on lambda by d. If lambda is depends on pressure, that is the gas property. If d is very small, then the viscous region extends up to 0.01 torr. Okay. There will be distribution of velocities within the pipe, because it is so narrow. Reynolds number comes into picture. Normally speaking, up below 1 millibar, you do not use these things. In viscous flow, effective pumping speed at very high pressures approaches the manufacturer's pumping speed, because conductances are anyway very high. So, it does not matter if you make a mistake of longer pipe or a shorter pipe or anything, instead of 3 minutes it may take 5 minutes, it will not take hours. But if you do this in ultra high vacuums, you will be in trouble. Okay. So, efficient pump down, the dimensions and of the interconnecting pipe has to be worked out by the engineer according to the process requirements and the constraints. If you do that, you will be able to decide proper pump, proper interconnecting pipe and predict the pump down calculations. And if it is not coming according to your predictions, you must think that there is a leak or some other parasitic load, accordingly you will work out. These things we will see in the next class. So, we have completed how do you calculate conductances, using that how do you calculate pump down curve. Thank you very much.